I'm very, this is my immense pleasure to introduce an eminent and dynamic personality, who is none other than Dr. Bharat Bhanvase, sir. He is the Dean, School of Chemical Engineering, Professor, Chemical Engineering Department. Lakshmi, his institute is Lakshmi Narayan Innovation Technological University, Amravati Road, Nagpur. He has contributed a lot in his academic and played a vital role, zestful excellence, and an indomitable spirit, along with an interdisciplinary, scientific, and applied research approaches. When I have gone through his resume, actually, he has really explored the curiosity and contributed a lot in the research domain. First of all, he has more than 22 years experience in teaching and research, and he has completed BE, ME, and PhD in chemical engineering successfully. Then his areas of interest is water treatment, solid waste processing, process intensification, ultrasound assisted process, microfluidics, nanofluidics, nanomaterials, and polymer nanocomposites, etc. He has more than 13 patents, 6 granted, and 07 in process. He has published several research papers in a scope of journals. Means more than 112 research papers he has published. He has also published 4 research papers in national journals and 112 research papers in international and scope journals. He has actively contributed in 17 international conferences, 12 national conferences, and he has also contributed book chapters in edited books. Book chapter number is 71. Very huge numbers. That is very useful for the researchers also. His publication 12 edited books. Then he has also contributed in process modeling, simulation, and environmental applications in chemical engineering, novel water treatment and separation methods, simulation of chemical process, CRC press. His next publication title is Nanomaterials for Green Energy, Encapsulation of Active Molecules and Their Delivery System. Then multifunctional nanostructure, metal oxide for energy harvesting and storage devices, CRC press. Then handbook on nanomaterials for wastewater treatment, fundamental scale up issues, 360 degrees waste management, 360 degrees waste management. Also photocatalyst for energy and environmental sustainability towards the nanofluids of large scale industrial application, bio-derived carbon nanostructure, fundamental synthesis and applications. He has authored a book. Its entitled is Nanofields for Heat and Mass Transfer, Fundamentals, Sustainable Manufacturing and Applications. He has guided more than 30 PG students and 2 PhD scholars have been awarded PhD degree under his supervision, and 6 PhD students are pursuing PhD under his guidance. He has also developed research and development projects, 6 completed, and one is pursuing, one is in process. Then he has completed 2 industry consultancy projects, and 2 is undergoing. He has contributed 111 for reviewer as a reviewer, international peer-reviewed for international peer-reviewed science journal. He played a very vital role as a review for more than 100 research papers, and suggested whatever the necessary corrections to the researchers. He is a fellow of Indian Institute of Chemical Engineering, and he has been awarded IA Chemical Weekly Award for Best Paper published in the Indian Chemical Engineer in its issue 2020, and also he has contributed for chemical engineering in the year 2025, 24, 23, 22, and he is a fellow of Maharashtra Academy of Science. He has been awarded as the Best Scientist Award from RTM Nagpur University, Nagpur on September 2017. He has been also conferred on Young Scientist Award from Science and Engineering Research Board, New Delhi. He has been also contributing as a Young Associate Fellow for Maharashtra Academy of Science. And as a research person, he has delivered expert talk on various topics as a keynote speaker, plenary lecture, technical session, chairperson, as an expert also in national and international conferences. More than 50 conferences he has delivered lecture, and he has attended more than 33 summer winter schools, workshop and conferences, and he contributed more than 21st workshops, courses and conferences organized, and he has also completed projects by AICTE, DTE, RTM, LIT University Nagpur. Really, sir, this is a very huge contribution in academic area that will definitely help the researchers, and today's lecture will also be useful to us. So this is a very brief introduction of Dr. Professor Bharat Bhanvase. Thank you, sir.
Thank you, sir. Am I audible?
Yes, sir, you are on.
Okay. Let me share the screen. Is it visible, sir?
Yes.
Yes, sir.
Yes. Okay. Thank you. Thank you, sir, for introduction, and thank you for invitation in this session. So I will just talk on nanofluids. So because we are working from 2015 in this area. So let me just minute. Okay. So first talk, I will concentrate on nanofluids in automobile sector, and how it will be useful in you can say in automobile sector. So if you apply the nanofluid, what is nanofluid? Then what properties you will get enhanced? with the addition of nanomaterials. And how can prepare that? I will put one case study also in this case. And in second talk, I will more concentrate on graphene material preparation, then role of ultrasound in that, hydrodynamic cavitation, and then stable preparation of nanofluid, and then its case studies that also we'll see. So then that is graphene based material that I will take as one sector, and this is another one. So in this talk, I will just concentrate on just introduction, then heat transfer mechanism in solid liquid and solid liquid interface, because nanoparticle, that is solid material which is dispersed in heat transfer fluid, which is liquid. So that part also we'll see. And heat transfer in solid, what is the mechanism there? Then heat transfer in liquid, what is the mechanism? Then solid liquid interface, how heat transfer takes place. Then different models we'll see, that is effective medium theory, extended effective medium theory, then Brownian motion, how this Brownian motion will be important, what are the fundamentals, then thermal enhancement, then different empirical correlations for that, then agglomeration and clustering as an enhancement model, liquid layering, that is another one, then thermophoresis. So these are the different basic fundamentals for the enhancement in the properties of nanofluid. And then we'll see applications as a case study in as a radiator coolant, engine lubricant, fuel additives, then automobile air conditioning, other different potential applications also we'll see. So that is the part here, and that I will cover in first talk. So if you see the introduction, so nanofluid, that first term that is coined by Chaos in 1995. So that was his paper in ASME, which was presented in 1995. So what he did, that is suspended micron size particles, right? So that was the old phenomena. So that has no doubt a lot of problems you will get if you have micron size or more particle size. If you have, then that will create a erosion, and pumping cost and viscosity will increase, and several problems you will get there. So what was the case here? So Chaos just introduced the particles in the fluid, and he observed that there is some improvement in thermal properties. So thermal properties, so that is very important again in heat transfer application. So by addition of this particle, he observes some improvement in these heat transfer properties, that means, or can say thermal properties. And if you use this large particle, whatever problems are there for with the micron size is there. So that means if you use large particle size, then it is very difficult to explain the theoretically, as well as then it's not reproducible. So that was the problem, and there are several problems in the design. That means larger particles will be there, then they will have impact in pumping cost will increase, erosion of pipe will be there, breaking up. That means that those are the problems. Then a lot of research have been done. If you see this nanoparticle is old, that means many people are working. Its production at large scale, pilot scale, it is already is there in market. These products are there, right? But addition of these nanoparticles, that was not explained. That means if you add these nanoparticles in base fluid, that is heat transfer fluid, that may be a water or ethylene glycol, right? So if you take your car radiator is having fluid, right? Earlier days, we used to add water, right? And then yeah, that will take up the heat from engine, and then cooling of that engine will take place. Nowadays, there is no need to open your car radiator, because that heat transfer fluid is smartly designed there, right? So that is ethylene glycol base. So so that is the case. So, but if you add some nanoparticles in such fluid, what will be the effect? That is the important thing. What property enhancement you will get? How that property enhancement will get? So that part we'll see here. So heat, no doubt, it is well known. Energy in transit, that is heat. Driving force will be a temperature difference, because with temperature difference only heat transfer will take place. And areas where heat transfer will have a role, that is energy demand. Nowadays you can see energy requirement, manufacturing processes, that means some cases evaporation is required, heating is required, so that is their recovery system. Then miniaturization is also there, that means small equipment, so heat transfer will be higher in such cases. Then where you will find heat transfer application, vehicle radiator is best example. Everyone knows this, because it takes the heat from engine and that is released to the atmosphere. So that is the part. Then you can say refrigerator is best example. Everyone has this. So that is absorbing the heat at low temperature level and rejecting the heat at high temperature level. So that is as per the second law of thermodynamics. Then solar system, solar heater, that means it will accept the energy. So water heating is done, so where heat transfer application will be there. Industrial manufacturing processes are there. Space and aviation is there. Electronic cooling is again very important. So that is another system that you can find. So electronic cooling, that means if you take your laptop, fan is running. So fan is what, for what purpose? It is just taking out the heat which is generated in the processor. Transformers, domestic heating, cooling. So these are the different applications for the heat transfer. So how we can improve the heat transfer rate? If you see the engine, motorcycle engine, two-wheeler engine, so outside portion of that engine is that is something like this. That is somewhat extended surfaces are there. That is called as pin, and because of that, heat transfer will be higher on outside surface. So that means if you increase the heat area, that means there would be increasing heat transfer. Another one is you can create a micro channel, small channel. That means what will happen? The diameter will be very small, right? And volume will be less, right? So, but surface area will be more. So heat transfer rate can be improved. That is one way where heat transfer can be increased. So what are the heat transfer fluids used in these processes? One is water, right? You will find in many application water is used in industry as well as a household application. Ethylene glycol is there, hydrocarbon oils are there, refrigerants are there, because your air conditioning is running on this. Phase change fluids are there. Phase change, that means it will during heating it will accept the energy and it will melt. And during release of energy, that means it will again give this the energy and it will solidify. That is a phase change. That is only latent heat of melting. So that will absorb. That's it. So if you see the fundamentals, already we know the conduction, convection, and radiation. So conduction, suppose if you see tightly packed material, solid. In the case of solid, what will happen? So these all molecules are tightly packed. That means heat transfer will be in sequence. That means from one molecule to another, like that. So it will be through the vibration of molecule, then propagating the phonons, and then diffuse free electrons. These are different applications here. Then another one is loose molecule. So that is your liquid and gas. In the case of liquid, distance will be there. So in this case, collision of between the molecule, that is very important for the transfer of heat from one part to another. Right. So then for gaseous system, again distance will be more. So heat transfer will be less, because for gaseous system, the distance between the two molecules is very high compared to the liquid. So you will find the thermal conductivity of gases is very less there. So if you see this gases is having thermal conductivity less than zero point 0.1 or less than 1, right? That is watt per meter Kelvin. For liquid, it is from, for water, so it is from zero point 2 to almost up to 10. So that is for, yes, that is for liquid. that is up to 10. Then more non-metallic solids, that is like ice or any other material. So that is again ranging from 0.8 to 100. And for pure, hello, sir. Hello.
Hello.
Sir, can you
Hello.
mute? There is some disturbance. Can you
हॅलो
mute?
विजय जाधव सर कोण आहे ते मध्ये डिस्टर्ब करताय हॅलो
Okay, we'll continue. Then if you see this for pure metals, so its thermal conductivity is very high. So if you see this for air, the thermal conductivity is 0.02. Then for helium, that will increase to the water, that is 0.61. And it will increase to diamond. Diamond is almost 2300 watt per meter Celsius. So that's how, that is for metal oxide or other things, so that you will find there is improvement in thermal conductivity if you go from gas to the solid phase. So if you have micro size and macro size particles, suppose that means macro size, that means if you have larger particle size, so here you will have one advantage, that is higher thermal conductivity, no doubt, but disadvantage, that is agglomeration, clogging, erosion in pipeline, right? Higher pressure drop. These are the problems you will observe with this. Then, so nanofluid is another that as we are discussing. So that is very important. That means here nanometer size particles are dispersed in the liquid, and these particles are suspended. So suspension, many times settling is observed, but for that you can have some surfactant and you can stabilize that. So these suspended particles in a liquid, that is called as nanofluid. So nanometer size particles, that is very important again. So no doubt Choice and Eastman, they have termed this in 1995, which will have higher thermal conductivity, large surface area, high stability. That was the intention, that was the objective for this particular nanofluid. So what are this nanofluid? That is, what are the advantages you will find? High heat conduction, that is one. Then stability will be more. Then microchannel heat transfer without clogging. That means if we have a small diameter pipe also through which that nanoparticle should pass, then reduce erosion, right? So pipeline will be intact. That means it will not get damaged, right? Reduction in pumping power. So that is another application that you will find. So theoretical framework, if you see heat surface, right? So here, this will take energy, right? And now this will collide with another particle. After collision, so that heat is transferred from this particle to this particle, right? So that's how that you can say heat transfer takes place in the fluid containing nanoparticles. Fluid, that means water or anything you can take here. And another one is movement of this particle, that will be motion. That means every particle, when it is suspended in water, it is in motion, right? So that is another way by which you can say transfer of heat will take place. So these are the different mechanism. If you see Brownian motion, that means every free particle which is present in gas or liquid, so that will take a one path and it will move in different direction like this, right? It is free to move. And during this particular, that is called as Brownian motion. So that is one phenomenon. That's how energy is transferred from one location to another location here, right? Another one is nanoparticle clustering. That is another phenomenon. So what happens? Your nanoparticles form a chain, right? Like this. So that's why heat transfer will take place in this particular direction, right? There is a heat conduction, you can say, right? Another one is nano layer. That means some solid-like layer is formed, right, around the nanoparticle, and that's how heated nanoparticle that means heat will be transferred from this nanoparticle to the fluid here, right? So then ballistic transport, that is because of non-local effect, thermophoresis, that is because of temperature difference, then near field radiation. These are the different, you can say, phenomena, mechanism by which heat conduction will take place in the liquid. So this is, if you see, heat transfer mechanism in solid, liquid, and solid liquid interface. If you see first, the Brownian motion, that is red color particles, if you see here, that is moving, right? So it will take different path here. And during its collision to another particle, it will give transfer the heat from one particle to another particle. So that is with Fourier law of conduction, right? So another one, so this is heat transfer in solid, that is because of vibrational, you can say, some rotate, that is movement of electron, phonon, right? So that is the case. So thermal conductivity can be calculated by, you can say, effective electron, then phonon, right? So all these will be added and then effective thermal conductivity can be calculated from this. So that is because of this vibration. You can see the moment will not be there in solid, but vibration is possible, and because of that molecular structure will be moving like this, and because of that heat transfer will take place. So another one is, this is heat transfer in liquid. So here some interaction between the molecule will take place. Here the collision is there. Suppose if you see, this molecule will collide with another, and then heat transfer will take place. Another case is the molecule will aggregate. That means they will form some chain inside the system, and then heat transfer can be there from one molecule to another molecule, like that. So this will be possible here. So that is the heat transfer in fluid. Then this is, you can say, solid liquid interface. Suppose this is the case. Here we have stationary nanoparticles suspended in water, and if you give some shock on one side, so then there is a moment of your particles and they will start colliding like this, and that's how that heat is transferred from one point to the another particle, another point. So that is, you can say, solid liquid interface part. So if you see the mechanism, already we have discussed this. Brownian motion will be there. Brownian motion, that means it will transfer that particle, nanoparticle will move in the liquid from in suspended manner from one point to another point to another. So that is the Brownian motion, you can say. Clustering of nanoparticle, already we have seen. So two nanoparticles will form a layer, and they will form a chain, and then heat transfer will take place from one particle to another particle. Then nano layering of liquid and liquid nanoparticle interface. So that is another one. So if you see this nano layer, that means we have this particle, and around that one layer is created, and that is conductive cover which is generated, and that's how heat is transferred from one particle, this particle, to the liquid and then another particle. Then ballistic transfer, that is because of, you can say, some shock wave. Then thermophoresis, that is because of temperature difference here. So if you see this effective medium theory that pertain to analytical and theoretical modeling that describes the microscopic properties of the composite material. So if you have different composite material and arrange in series or parallel, right? So its thermal conductivity can be calculated in these by using these equations, and that is well presented by Maxwell's in, you can say, 1873. So if you want to observe this Brownian motion, see, this is one particle, right? How it is moving in this phase here, right? So in this case, so this is moving, it is taking path, and no doubt collision will be there. So that means this particle is moving with respect to position and time, right? So that is the case. So that means two dimensional. That's why this is that function that is changing with respect to time as well as with respect to position. At the same time, your diffusion, so D, that is very important. So if you see this agglomeration and clustering, so if we have this one cylinder and if you add some nanoparticles, no doubt if it is stabilized by surfactant, after some time you will observe these particles are moving and they are forming some chain-like structure here, right? So that's how, after forming this chain-like structure, so heat transfer can be taken place from one particle to another particle, which are arranged in that sequence. So that is the another case. So initially we have separate nanoparticle, but another aggregates are formed. So this is one aggregate, another aggregate, like this. So it will form a chain like structure, right? So that is because of weak van der Waals forces which are present there. And no doubt if you stir or if some apply force, so that will get separated. So this is nano layering, liquid layering that will heat transfer enhancement. So what happens here? Nanoparticle is present inside, and around this, all these particles are arranged in sequence, and that is something like having some crystal structure, like you can, that is crystalline layers, something like that, and that is why you can say 1 to 5 atomic layer, and it will have very high thermal conductivity than liquid, right? So that is another mechanism by which you can say heat transfer that can be improved with the use of nanoparticles. So this is thermophoresis. You can say with increasing temperature, no doubt it's every particle will accept that energy, and its energy will increase and its movement will be fast. So bombarding of these nanoparticles on each other with increasing temperature will be higher than decreasing particle. So another case, if you see, if you go ahead, that is all fundamentals already we have seen, right? That is, you can say Brownian motion, then nano layering, thermophoresis, right? Well, that is nanoparticle clustering, right? So that part already we have seen, and now we have classification of nanofluid. How we can classify this? There are two. Nanofluid is nothing but you can say addition of nanoparticles in water or ethylene glycol, or that is liquid. So solid particles are added in liquid. So here, if you use only one nanoparticles and that is suspended in water, that is called as mononanofluid. That means one type of nanoparticle. Just like copper oxide is dispersed in water, right? Only copper oxide, that is mono, right? But in hybrid case, what happens? That is combination of different nanoparticles or nanomaterial that is added in the system. Just like you can say graphene and loaded with suppose Fe3O4 nanoparticles, right? Or some composite material which is prepared and that is dispersed in water, right? So that is you can say hybrid nanofluid. So hybrid nanofluid will be a mixture base, nanomaterial mixture base. That means you can have TiO2 plus copper oxide. That mixture of nanoparticle is added in the base. And another one is nanocomposite base. Composite, that means we are adding, that means we are depositing some nanoparticles on support, just like graphene, right? And then it is added in base fluid. So that is forming, you can say nanofluid. That is called as nanocomposite base nanofluid. And first one is nanomaterial mixture based nanofluid. So that is the classification you can see. So what are the applications you can find here? So applications are wide range of applications you will get here. So that is starting with in heat transfer, heating, cooling, thermal management system, refrigeration system. Nowadays, nano refrigeration concept is there, right? Many people are working on this concept. Then solar thermal system. We have one project now from Maharashtra Energy Development Agency of 1 crore, and we have installed 100 kilowatt solar panel system where we are applying nanofluid for heat transfer purpose here. Then extraction of energy from sources. That means in such cases, material selection is very important. Remember, nanoparticles, how we are selecting, that is very important. So nanoparticles, what we have, so that should be dispersed properly in the system, right? So here, well, you can say the dispersion is okay. One more point is when you are saying extraction, that means uh, how that means energy is taking from one suppose solar system. So it should be able to take that energy very fast, right? And then it is transferred. And if you want to store that, then heat capacity of that nanoparticle should be very high. Then only it will store the energy. So that is another application you can say. So nuclear reactors where high amount of energy is generated, so it can be used, right? Then in mass transfer application, that is related to chemical engineering. Other application, tribiological application, that means Tribiological, that means you want to suppose decrease the friction. So many times grease is used or oil is used to reduce the friction. But if you add some nanoparticles in that oil or grease, that will again improve the that properties. So you will have better material then. So that is tribiological application. Then antibacterial application. So antibacterial, that means by adding the nanoparticles like silver nanoparticles, that will kill the bacteria which are present in the system. Medical application will be there. Then sensing applications. These are the different applications that you will find. So what are the components that will be used in nanofluid? One is base fluid, already we have discussed. Base fluids, you can say water, ethylene glycol, engine oil, acetone, decane, propylene glycol. Many are there, right? In this base fluid, that is water, or in that we are adding nanoparticles. So what are the different nanoparticles? One is metallic, copper, aluminum, Fe, Ag, Au, that is gold, or you can say silicon. Another you can say oxide base, Al2O3, is copper oxide, TiO2, SiO2. So many people have worked. Then you can say carbon base, we have CNT, fullerene, graphene, then nano droplets. Then another part is surfactant, because many times these particles get settled. So in that case, we need to add some stabilizing agent, that is sodium diatoxide sulfate or CTAB or gum arabic, or you can say CMC, right? Other surfactant also you can add based on the material what we have selected. So preparation of nanofluid, if you see, so this is one case study I'm putting here. Suppose one step method here. One step method is what happens? Suppose I want to disperse copper oxide here, right? Copper oxide. So for preparation of copper oxide, what type of you can say precursor, that means reagents are required for the preparation of copper oxide. So what I will do, these precursors will be added. That is first reactant. This is second reactant. These two reactants are added to the system, and then reaction will take place here. And during reaction, copper oxide is supposed form, and this copper oxide is in nanomaterial size. So that is suspended in the system, right? And same system will be used as a nanofluid. That is called as one step. That means only one step. That means reaction is taking place, and whatever nanoparticles are formed, same it is used for as a nanofluid. But what are the drawbacks here? Drawback is nothing but whatever impurities are formed because of reaction, that means byproducts or some unconverted material, right? So that will remain as it is in the system, and no doubt that will affect the properties of the nanofluid. So how it will be then? There are many that means many methods are available for the preparation of such type of nanoparticles. So solvothermal, sol gel, then you can say microwave, ultrasonic, phase transfer, right? So many methods are available, physical as well as chemical methods. So that can be used here. Two-step method for the preparation of nanofluid. It is very simple. What we are doing here, first we have to carry out the synthesis of nanoparticles, right? First nanoparticles, then drying of that nanoparticles, and then you will get pure nanoparticles, no impurity here. And then you add a base fluid as water or ethylene glycol. At the same time, you add some surfactant. Nanoparticle is added here, and that will be the formation of nanofluid. And that is by two-step method, right? So in two-step method, step one is your nanoparticle synthesis, is very important. And second step is dispersion of synthesized nanoparticles in a base fluid, right? So that is again very important with the addition of some surfactant, no doubt. So then dispersion method you can see with the addition of surfactant, dispersion homogenizing or magnetic stirring, ball milling will be there, ultrasonication will be there, cavitation based hydrodynamic cavitation process will be there. So different combination of methods can be used for homogeneous suspension of these nanoparticles in the system. So that is required. And this is, you can say, two-step method for the preparation of nanoparticles, sorry, nanofluid. So one step we have already seen, and this is two-step. A difference here, you can say, in one step, impurities will be more, right? Because after reaction, unreacted material or some byproducts which are formed, that will remain as it is there in the system. And in two-step method, advantage is you can say first pure form of nanoparticles are suspended in the nanofluid. So that is the difference what you will get here. So nanofluids, if you see, what are the different studies which are related to this nanofluid? What type of study we can carry out? One is you can say preparation of nanofluid by one step as well as two-step method, right? Once it is prepared, then we have to check the properties of nanofluid. Properties of nanofluid, what are the properties that you can check? One is thermal conductivity of nanofluid we can check. That is a transient hot wires concept that you can use. And for that, KD2 Pro instrument is available. With this, you can use, you can calculate the thermal conductivity. Then another one is viscosity. So for that, you can have some viscometer or rheometer or rheological property also we can check, right? So another property, if you see, that is density of that nanofluid, right? So that you can measure by density bottle also can be used, or density, some density measurement instrument is required. Then specific heat, CP value, and then surface tension. So that can be calculated. So these all 5 properties are very important for nanofluid, which are required because based on that only we can design the system, application system. So what are the applications you can carry out the experimental studies on nanofluid? That is one experimental study, that is heat transfer application. You can select coil type of heat exchanger, or you can say straight tube of, or in micro reactor you can study the heat transfer, right? Micro system, right? And then theoretical studies, that is that we have to see based on the experimental data, empirical correlations can be done. So such as you can say relations for thermal conductivity, relations for density or viscosity or specific heat. So that can be generated, or some theoretical studies can be calculated. You can put some heat transfer, heat energy balance equation or material balance equation. So some theoretical studies can be calculated here. And then some heat transfer applications also you can see. We can say in solar system, or you can say transformer, right? So many applications as we have discussed earlier. So that can be done here. So that is, you can say, part of nanofluid. So why there is a need of research? Many people are working on nanofluid. Why there is a need? Because so we need to identify what is the enhancement in the heat transfer with the use of nanofluid. That is very important. That is, by adding nanoparticle, how much enhancement is done. It is possible. Then we have to see some theoretical models that will predict the behavior of nanofluid, such as properties, thermal conductivity, viscosity, right, or density, right? And no doubt we have to see the optimum set of properties from this to maximize the heat transfer, and thus promotes the energy conversion here. So another one is, see, if we have nanoparticles of different size, shape, different types, that is 1D, 2D, 3D nanoparticles, right? 0D, as well as its concentration, composition. So that will affect the base fluid on its dispersion or its properties. And different different properties that will alter, that will change, right, with the addition of nanoparticle, that is thermal conductivity, viscosity, density, heat capacity. So that is very important, that we need to see how it is getting changed with respect to addition of nanoparticles. Then effectiveness of heat transfer processes employing nanofluid also depends on various flow geometries and conditions. Then some applications proposed for the nanofluid require uh, mathematical support and simulation in order to interpret their actual behavior. So what are the gaps in study? See, more research on is on fundamental than industrial application. So that means many fundamental studies are done, but industrial applications are many missing there. Then various geometries, lab scale heat exchangers, right? So solar and refrigerator setups, that study is needed. Then study of agglomeration, settling, erosion by the use of nanoparticles. So that need to be examined in detail, right? Optimum set of properties that we need to see, right? So yet to define that is particularly nanofluid, that is stability, size, shape, temperature, preparation method. All these will affect the properties at the end. Then optimum point of increase in thermal conductivity versus viscosity, because the addition of nanoparticle will increase the viscosity, right? That is harmful, that is not required, right? That means with addition of nanoparticle, thermal conductivity improvement is necessary, that is required, but at the same time viscosity should be in control. So that's why you have to see the what amount of nanoparticle should be added in the system, that we need to see. Then effect of pH on the performance of nanofluid, that we need to see. Then lack of correlations for pH, because no doubt pH will affect, that means acidic or basic medium, that will affect the stability of nanofluid, right? Then different common correlations for nanofluids, lack of correlations for hybrid nanofluids, so that that fundamental research can be carried out by using this. Then effect of nanoparticles on hydrodynamic and boundary layer theory, the boundary layer thickness, so how it will change and how it will affect the heat transfer properties. Then relation between heat transfer and friction at the fluid walls interface, right? Then nanofluid stability at different flow condition, nanofluid behavior at transition flow region, that is laminar, turbulent. So that also we have to see, right? So copper oxide and Al2O3, many people have studied. Other nanoparticles we need to see, right? So many are there. So you can see different part, that means some theoretical studies also you can do, CFD, computational fluid dynamics, and all this that can be done again, right? So one case study I will put on this, and then uh, another part I will see. So what we did, we have prepared AG-dope Ep3O4 nanoparticles in the lab, and those are dispersed in water as a heat transfer fluid, right? And then that heat transfer study was in pinch pipe. Pinch pipe is, I will show how it looks like. So in this case, what we have done, we have prepared that means we have to see the desired structure of nanoparticle is very important here. The synthesis process that we need to consider here. So Ag-dope Ep3O4 nanoparticle, that addition, that will create a composite, and that composite was prepared by ultrasound assisted technique and micro reactor. Micro, that is very small reactor we have used for the preparation of nanoparticle, and its synergic effect was studied in this case. So what is the methodology what we have used? That is synthesis of Ep3O4 nanoparticle, right? So that is done. Ep3O4 nanoparticle synthesis can be carried out by using FeCl2, FeCl3 addition, and then you can say ammonium hydroxide can be added in that. So that will lead to the formation of Ep3O4 nanoparticle. This form Ep3O4 nanoparticles, these were dispersed in reaction medium, and then AgNO3 is added, and then sodium borohydride. So that will lead to the Ag-dope Ep3O4 nanoparticle. Its characterization is done by XRD, FT, IR, then other techniques. And then preparation of nanofluid is done, and then stability test was carried out. Then thermal conductivity measurement was done, density measurement was done, and then convective heat transfer and pressure drop study was carried out for this case study. So if you see the experimental part here, so FeSO4, FeCl3, that is addition, then NaOH was used, AgNO3 was used, sodium borohydride was used, right? And then sodium trisodium citrate dihydrate, that was used as a surfactant. So what we did, FeSO4, FeCl3 is added, that mixture was done, right? And then it was sonicated in a bath sonicator, and then addition of NaOH was done here, right? And this ultrasonication, after addition also ultrasonication was continued, and after that filtration, and then that will lead to the formation of Fe3O4 nanoparticles. So that was done in lab, and here we have taken some amount of Fe3O4, that is 0.2 gram, then it is sonicated for achieving the dispersion, proper dispersion, and then trisodium citrate dihydrate was added here, so it will stabilize the particle, and then uh, we have added some, you can say, sodium borohydrate here, and then dropwise addition of AgNO3 solution was carried out. So that's how what happens on the Fe3O4 nanoparticle, deposition of Ag nanoparticle takes place, right? And then after filtration, you are getting Ag dope Fe3O4 nanoparticles. So we tried at different sodium borohydrate concentration as well as surfactant concentration. So this is the setup for the preparation of nanoparticle in syringe A, B. The first one was with ultrasound, only ultrasound, right? This was done with microreactor. So syringe 1, A, B, C, right? That we have taken, and this all material goes inside, and that is flowing inside, and during its flow, reaction takes place, and you are getting nanoparticles at the end, right? So this is your geometry. You can say length of this reactor is 1.79 meter. Uh, then diameter, inside diameter is 2 mm, right? Outside diameter is 5.5 mm. So that was there. And this is the setup what we have used. And in syringe A, we have used uh, 0.2 gram of Fe3O4 nanoparticles, which was sonicated in the presence of sodium citrate, right? And flow rate was maintained 200 ml per hour. Then in syringe B, we have added AgNO3 solution, that is 0.01 molar, with the flow rate 100 ml per hour. And in syringe C, sodium borohydrate solution with different concentration that was tried in lab, which was done at 100 ml per hour. So syringe A is your Fe3O4 nanoparticle with surfactant, B is with AgNO3, C is with sodium borohydrate, and as soon as it enters here, reaction start, and during its flow, crystal growth takes place, right? Crystal, that means deposition of Ag will be there, and by the time it comes out, so that is dope material formation is there. So that was characterized by UVBs, then FTIR, XRD, and TM analysis, right? And nanofluid preparation was done by two-step method because Ag dope Fe3O4 nanoparticles, what we have prepared, that same we have dispersed in water with the help of ultrasonication. So it is well dispersed in the water. Then we have carried out the stability test by using sedimentation method. For that, different concentrated nanofluid was prepared, and that step was carried out for 2 months, and we have taken that photographic evaluation we have done here. For thermal conductivity, we have used uh, uh, thermal property analyzer, that is the, and then at different concentration, that is thermal property analyzer was used for the measurement of thermal conductivity, and concentration of nanofluid is 0.01, 0.02, 0.03, 4, 5 volume percent, and temperature was varied from 25 degree to 45 degree Celsius, and percent enhancement in thermal conductivity was calculated by thermal conductivity of nanofluid minus thermal conductivity of base fluid divided by thermal conductivity of base fluid. That is simple relation which was used for the calculation of thermal conductivity. So density measurement was done by density bottle with same concentration of nanofluid at room temperature, and relative density was calculated there. So this was the experimental setup which was used for the heat transfer study. This is a pipe which we have used, right? This is a pipe, and here we have put thermocouples for measurement of temperature at the surface as well as inside that fluid which is flowing here. And these are recorded, right? And pressure drop also calculated by YouTube manometer. And this is setup. So after calculating these temperatures or measuring the temperatures at inner wall surface as well as inner wall and base fluid. That means we have to measure temperature here and here, center. And we have to take a difference between these two, right? So for the calculation of heat transfer. So this is pinch tube. Pinch tube, that means you can pinch. That means you have a circular pipe, right? What we have done here, we have pinch. That means we have to apply some pressure, right? And then then this type of structure is formed. And alternatively, this side, and then it is rotated like this and like this. So this is the holder thermocouple and center as well as surface we have calculated. And all these details are provided here. Then convective heat transfer study was done for two concentrations, 0.01 and 0.02 volume percent, with Reynolds number ranging from 2050 to 6160 here. Then thermal density was measured by this, calculated by this relation also, where phi is volume fraction, rho BF is density of base fluid, and this is the density of particle. Similarly, heat capacity was also calculated from heat capacity of base fluid and heat capacity of particle, and phi is a volume percent. So heat transfer coefficient was calculated by using this. So heat flux, that is surface temperature minus bulk temperature. Heat flux was calculated by this equation, that is m dot Cp, Tb0 minus Tbi upon A. Nusselt number was calculated, which is these are the different parameters which are very important in heat transfer study. So that is in chemical engineering, you will observe this, right? Then pressure drop calculation was done by delta H rho G, and which was done by Darcy-Weisbach equation also. That is friction factor was calculated from this, from delta P. That delta P you can submit here, length of pipe, velocity, density, and diameter. So from that you can calculate the pressure drop. So this is the mechanism of, we can say, AG dope Ap3O4. You can say first we have prepared Ap3O4 by using ultrasound assisted method. Then we have added some surfactant. That citrate surfactant is forming some functional group on these particles. And then Ag particles is coming and it is deposited here, right? And with the addition of, you can say, with the presence of sodium borohydrates, there is a formation of nanoparticles in this. Formation of nanoparticles in this. So that means suppose we can say Ag dope here, Ag dope Ap3O4, then it's nuclei, then after growth. So this complete Ag is deposited on Ap3O4. This is the, you can say, mechanism what we have proposed. So here advantages of ultrasound, you can say better contact between the reacting species. Then exposure of Ap3O4 nanoparticle would be very good. Then distribution of Ag, right, over the surface. Okay, that is uniform distribution of Ag over the surface of Ap3O4. So that is the formation of, you can say, Ag dope Ap3O4 nanoparticle. And microreactor, or we are calling this as a mini reactor. So it is the same thing again. So here we have small reactor diameter, so adjustment in flow, continuous flow will be there. So continuous synthesis of dope material is possible here, right? Reduced time, so in lesser time, formation of Ag dope Ap3O4 nanoparticle is there. These are some advantages here. And if you see the UVB spectrum, you will observe that is Ap3O4 nanoparticle spectrum, which is prepared in different cases. One is Ag dope Ap3O4 at different ratios here, right? That is sodium borohydrate to citrate surfactant ratio that we have tried. And the peaks which are essential there, that is peak at 277 or you can say 294. So that represents the formation of this material successfully. FTR also we have carried, we have seen different functional groups which are presented, right? Prepared by ultrasound assisted method, microreactor system at different ratio, right? We have carried XRD analysis also. We can see this XRD analysis at different ratio, right? And the particular peaks which are present there, that will confirm the formation of Ag dope Ap3O4 nanoparticles, right? So that is the, with ultrasound as well as in microreactor. So this is a comparison, right? So first one is And one more thing we have tried, that is microreactor plus ultrasound also we have done. That means microreactor was placed in ultrasound bath. So this is microreactor with ultrasound, and this is prepared with ultrasound. So you can find out with the use of microreactor, the crystallinity of the material is increased here. So you can observe the sharp peak here compared to the ultrasound assisted method. So this is the TM analysis. You can check. This is for Fe3O4 nanoparticles, right? So you can observe the particles are less than 50 nanometers. So particularly if you see the histogram, the average particle size what we observe, that is 11.3 nanometer, which is produced in this. This is for Fe3O4 nanoparticles. But if you see the AG-dope Fe3O4, right? So this is another one. So you can see Ag doping is there on the these particles, and then we have carried out the stability test. So this is initial condition at different volume percent. After 1 hour, you will observe settling, right? This is for the case of only Fe3O4, which is dispersed in water, that is water-based Fe3O4 nanofluid. Then settling continues after 24 hours. You can observe this, and then, but after 3 weeks, complete settling was observed. So that's why you can say Fe3O4 nanoparticles, even if it is in smaller size, its stability after maybe 24 hours or like that, so that gets decreased. So for Ag-dope Fe3O4, you can say nanoparticles, nanofluid, which is prepared by ultrasound assisted method only, you can see stability is very high, right? So it is initial condition. If you see this after 48 hours, after 4 days, after 6 days, after 1 week, then after 2 week, 3 week, after 3 week, I think after 6 days, some little settling is there. See, you can see some clear liquid you will get. So settling is there. So like that, and after 4.5 week, I think you can observe literally it is having good stability. If you see this ultrasound, that is Ag-dope nanocomposite or nanomaterial, which is prepared in mini reactor, that is ultrasound assisted mini reactor. So it is observing higher stability here, right? After 6 weeks also, you will observe the nanofluid is stable here. So stability study was carried out here, and you can observe this is at different volume percent. So 0.1, 0.2, 0.3, 4, 5, 0.1, like that, right? So here one phenomenon is observed in its primary stable period. This is a primary stable. After that, settling is observed, right? After that, settling is there. Then stability regaining period. Regaining, that is what happens, some cluster formation takes place, and that will again improve the stability. That means some forces gets balanced. That is interactive forces between the nanoparticle gets balanced, and you will observe the complete stability after this. That is secondary stable period. But Fe3O4 is unstable, right? So settling period is there, so no doubt. But with the addition of Ag-dope material, so settling gets improved here. So from that, we have just predicted some mechanism. So this is initially stability, right? So no doubt this is energy barrier is calculated between the two particle, right? And after that, once that energy is suppose balance, that means in that case your unstable period will be there. That means, right? So that is the case, but another unstable, and then it will continue. In the case of Fe3O4, we observe. But another case is secondary, some redispersion of these clusters was observed, and that is nothing but your secondary stability period. That was done. Then we have measured some thermal conductivity as a function of concentration of nanoparticles at different concentration. We have calculated at different temperature also we have done, right? And we observe that with addition of nanoparticles, right, then thermal conductivity gets improved, right, with the addition of nanoparticle as well as with the addition of with the increasing temperature, both. So that is the case here. So you can observe this. In the case of azidope, some interesting phenomena was observed here. When we are measuring the thermal conductivity at lower temperature, we observe higher thermal conductivity, and then with increasing temperature, it is decreasing first and then increasing, right? So that was the observation we got in the case of azidope Fe3O4 nanoparticle prepared by ultrasound assisted method or in microreactor. Same case here again. So it is same observation. So you can see the thermal conductivity here, which is where calculated, and you can observe that at 45 degrees Celsius, highest thermal conductivity will be there. And with no doubt, with increasing the volume percent of nanoparticle, thermal conductivity gets improved here. Then convective heat transfer study, we have calculated Nessel number. Already we have discussed some correlations in previous slides. And from that, we have calculated. So at different position in the reactor, in the heat transfer tube, we can calculate the heat transfer. So it is observed that with the increase in, you can say, Reynolds number, the thermal conductivity gets improved here, right? This is for 0.01%. This is for 0.02% volume percent. That nanoparticles we have added in the base grade. So that's how it is improved here. So this is at different Reynolds number we have calculated. Then this we have, this is in microreactor azidope Fe3O4, right? This is also azidope, but in a mini reactor with ultrasound, so that we can see. And you can see the comparison here. For Nessel number for water, it is less. In the case of Fe3O4, it is improved. Then azidope Fe3O4 by ultrasound, it is improved. And azidope Fe3O4 prepared in ultrasound assisted microreactor, again it is improved. And this is observed in all cases, you can check, right? So that is the case for 0.01 volume percent as well as 0.02 volume percent. So that's why that shows the in microreactor with the use of ultrasound, some crystalline material is formed, right? And that is more effective in the transferring the heat, which will have higher thermal conductivity, right? That material is properly formed, right? And that will help in enhancement in the heat transfer application. So further, we have calculated some pressure drop calculation. You can see this for two cases we have done, that is 0.02 and 0.01 volume percent. So these two, and this is a pressure drop, and this is your friction factor. You can see that the friction factor gets reduced with the addition of nanoparticles. So that is called a shear thinning phenomena. If you see the rheological properties, with the addition of nanoparticles, some cases if you apply the pressure, viscosity decreases. There are some cases where by applying pressure, viscosity increases. Where viscosity increases, that is shear thickening. Where viscosity decreases, that is shear thinning. In this case, shear thinning phenomena is observed here. So now coming to different applications, suppose if you use, so these nanofluids can be used as a coolant in car radiator, right? So internal combustion engine, so this is a radiator here, right? This is airflow, right? This nanofluid will flow like this, it will come to the engine, right? So it will take the heat from that and again it will reject there, right? So that is the case here. So nanofluid will improve the heat transfer rate here and your engine efficiency can be increased. So we can use this nanoparticles that can be added in engine oil, right? Engine oil that will improve the lubrication effect in the system. That is one application. Another one is with the addition of these nanoparticles, sometimes what happens, that will act as a catalyst in the flow, in the chamber, piston chamber, right? Where fuel burning is there. So that will improve. So as a catalyst, so it will that means convert your fuel completely into carbon dioxide or water or something like that. So there is no formation of, you can say, carbon monoxide like that. So that is black smoke. What we are getting, that is carbon monoxide. Then this can be you can add this nanoparticle as a fuel additives. If you add this, as I have discussed, it will act as a, you can say it will have some catalytic activity. So that will help in converting your fuel completely in, or you can say complete combustion can be ensured by the adding these nanoparticles here. Then in air conditioning, also nowadays we are calling this as a nano refrigeration, right? So in this case, in a compressor, whatever oil is present, there we are adding some nanoparticles, and that will improve the efficiency of this refrigeration system, right? No doubt people have tried this at lab level, but at industrial level or actual case, it is still pending. Many people are working on this, right? Then other potential application of nanoparticle, as you know, it is applicable in polymeric nanocomposite. You can use as additives in fuel cell batteries for the preparation of electrode material, right? Or membrane material in the fuel cell or in batteries, right? Then nanoscale sensor material can be prepared by using these nanoparticles, right? Then you can say catalyst, different catalyst preparations are possible. Nanoparticles can be added in during the preparation of tire, so that will have more strength for the tire also. Nanocomposite coating industry, it is very important. See, everywhere paint is there, coating is there. In that, we are adding different nanomaterials, nanocomposites that will improve the coating efficiency. Anti-corrosion as well as its mechanical strength increases, impact strength increases, right? After impact also that coating will not get disturbed. Heat shielding is there, nanofilm, self-cleaning is there. Self-cleaning phenomena is also there. That means if you have super hydrophobic surface, that means suppose if you have kitchen sink and if it is coated with super hydrophobic material, right? Whatever dirt, food material or that waste material is there, it will not stick to the basin also. So that is good application. That means that type of thing. That means so cleaning effect will be very that means efficient. That means it will be good here, right? So that is the case here. Then in conclusion, I will see conclusion there is some no doubt nanofluid is very important. Nanoparticle synthesis is very important. What methods we are using, that is again very important. That will help in enhancement in thermal conductivity. Different physical properties gets changed like density, then surface tension, or you can say viscosity, thermal conductivity. And these properties are very important in the, you can say, in heat transfer application. But still, some reliable experiment must be carried out to see this physical inside, right? We have to see the agglomeration models. If agglomeration is there, so how it will behave, what properties you will get, uh, properties of nanofluid you will get, right? Some molecular simulation can be appropriate for this. Heat transfer application, so that we should see in different application. We have to see the different application, solar system, or you can say car radiators, or you can say refrigeration system, where you can apply and you can experiment this, right? So that will be a topic of research. Then friction factor, we have to see how much friction, so what is the pressure drop calculation. So all these are very important from engineering point of view. Then at the same time, some challenges for nanofluid. So that will be scale up capacity. So can you prepare the nanoparticle in large quantity? So that is very important aspect. So with having similar size, shape, monodisperse nanoparticle, then we have to study the temperature effect also. That is very important. Addition of surfactant. Many times surfactant addition will have some negative effect also. That also we need to see. Then nanoparticle influence, Then cost of nanoparticle, that is very important. So it is costly. Interfacial increasing the viscosity, that also we have to see. Nanoparticle influence, that is loading, dispersion, then stability, agglomeration, type, size, shape. All these effects can be studied, right, to get the output from that. Or that is the research point, research problems. So somebody can take up these problems and can work in these areas. So thank you for first session here. This is our book, which was published in elsewhere, Nanofluid for Heat and Mass Transfer, Fundamental Sustainable Manufacturing and Application. So I have written this with the book with my PhD student, Divya Barai. So thinking if you have any question, I will take up this. Hello. Hello.
Hello, sir.
Yes.
Dear participant, if you have any questions, the session is open for discussion. You can ask
Hello,
any
sir.
questions without any hesitation.
Yes.
I am Dr. Mote, sir.
Yes, sir.
You explain a very nice lecture in case of nanoparticles,
Yes.
and you think as a coolant in a four-wheeler,
Yes.
how it work as for
Actually, what
benefit?
happens, sir? We are adding some coolant in that system, right? Nowadays, in different car radiators, it is there, and
Okay,
they are
sir.
using now they are using, I think, ethylene glycol. Right?
Yeah.
It is well designed. Earlier, if you have seen, पहले हम पानी डालते थे, थोड़ा सा दूर चलो, पानी फिर से डालो, like that. Old cars, right? But
Okay.
nowadays, that coolant is nicely designed. You can see there is no need to open that car radiator for maybe 10 years or something like that. But that is again can be improved by addition of nanoparticles.
Yeah.
So
Thank you.
if you improve that, the size of that heat exchanger, that car radiator can be decreased, and again you will have more space in the car. Yes.
Thank you, sir.
Anyone else, please? Okay.
I think there are many people from different background, right?
Yes, sir. Yes, sir.
Okay.
Some
So
people are from humanities also, science also.
actually, I have taken from engineering and science point of view. So I tried to explain for humanity people also, but let's see how it is transferred to them, or okay.
Yes, sir. It was very nice session. It was very lucid and informative session, and you really tried to explore each and every point regarding to nanofluids, engineering points of view. Then reliable experiments, what are the challenges, methods, methodologies, moleculars, and all. Uh, and I hope your lecture will be useful to one and all here.
Okay, okay, sir.
So it is also important to explain each and every point by making it in simple words, using the research and innovative point of view. That's why I would like to say it's very incredible and innovative. And that's why you try to apply interdisciplinary approach, scientific approach, and engineering points of view also towards the subject here. So
Yes,
I
yes.
wish you thank you on behalf of Dr. Babasaheb Ambedkar Maratha University for delivering such an expert lecture. Thank you very much, sir.
Thank you, sir. Is there any next session?
No, sir.
So there is only one,
Yes.
right? You told me that
Tomorrow we have another
tomorrow
session on tomorrow.
my session.
No.
That is only one session I have to deliver
Yeah,
twice, right?
actually, Gaurav
Because
sir.
your letter shows 3 to 4:30 and 4:30 to 6.
Let me confirm, sir. Let me confirm. Hello,
Yes.
Gaurav sir. One minute.
Yes.
Hello, sir. This is the last session, sir. For
Okay. Thank you, sir. So should I leave
so,
now?
hello.
Should I leave then?
Yes, sir.
Okay. Thank you, sir.
Okay, thank you, sir. Thank you for
Okay.
your contributions.
Okay, sir. Thank you.
Hello. Is there any session after this or not?
Excel we wait करा
Hello.
5 minutes.
Okay, we are waiting.
Hello, all participants. Hello.
Sir wait करा sir 5 minutes.
We are waiting. We are waiting.
हम्म. तर थांबायचं का आता आपण म्हणजे हॅलो हॅलो थांबायचं काय म्हटलं का थांबायचं
Wait 5 or 10 minutes.
सर वेट करा 5 मिनिट्स.
Okay, okay.
ठीक. हो. और पार्टिसिपेंट पूछना है कि ऑलरेडी अभी जो लेक्चर सर का चालू था तो अभी वही 10 मिनट का ब्रेक दिया सर ने. अब फिर से अभी लेक्चर 4:40 को स्टार्ट होगा. नंबर 8.
येस सर
सरांचा लेक्चर संपला नाही सर. सरांचा लेक्चर आहे.
मग मला सरांनी तसंच का बरं सांगितलं
काय रे सर.
की मला सरांनी सांगितलं की ऑटो ट्रान्स करून वेंड अप करा म्हणे
नाही 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 सरांनी आय थिंक सर कन्फ्युज झाले होते. सरांना कळालं नाही नेमके लेक्चर डबल आहेत म्हणून.
अच्छा
सरांना फोन केला मी. फक्त आता काय नाही, आता फक्त सर स्टार्ट करतील आणि डायरेक्ट आपलं फक्त वोट ऑफ थँक्स करायचं 6 वाजता.
बरं ठीक आहे चालेल
येस ओके थँक्यू.
चल
एक 10 मिनिटं ब्रेक आहे. 4:40 तास जॉईन होते.
ठीक आहे चल
हॅलो सर. हॅलो सर.
सर 10 मिनिटाच्या ब्रेक साठी गेलेत सर.
पण पुढचा सेशन होणार आहे की नाही ते तर म्हणाले सर परत येणार वोट ऑफ थँक्स करायचं आपल्याला. मग व्हॉट अबाउट नेक्स्ट सेशन?
सर लेक्चर स्टार्ट होणार
नाही
आहे 10 मिनिटांनी.
ओके
नाही
ओके
10
सर,
मिनिटाने
थँक्यू.
सुरू होणार आहे ना.
अच्छा, मला वाटलं की ते सर म्हणाले ते परत येणार आहे, वोट ऑफ थँक्स करायचं राहिलं वगैरे, आणि म्हणून म्हटलं पुढचा सेशन आहे की नाही नक्की काय असं. हरकत नाही.
हॅलो डॉक्टर. हॅलो डॉक्टर मोठे सर. हॅलो डॉक्टर मोठे सर.
सर पीपीटी शेअर करू शकता सर.
जस्ट मिनिट सर. दिसतंय तिथे?
Yes, sir.
Is it visible?
Yes, it is visible.
Yes.
येस सर.
Okay. So हे थोडंसं वेगळं आहे. That means graphene material that we'll see. Its preparation and roll up ultrasound that we'll see. ठीक है. Should we start?
Yes, sir. You can start. Sir. You can start.
Just a minute.
तर थोडं मराठी पण सांगा सर.
हो चालेल मराठीतून. ओके सगळे
जास्त
क्राऊड आपलं
मरा-
मराठीतच आहे.
जास्त महाराष्ट्रामधले आहेत सर प्राध्यापक.
ठीक आहे चालेल. ओके.
हो.
ऍक्च्युअली हे कसं सायन्स आणि इंजिनिअरिंगचं असल्यामुळे थोडंसं
हो,
ह्युमॅनिटीसाठी थोडंसं वेगळं राहील.
हो सर चालेल.
राईट
थँक्यू सर.
राईट. ओके ओके. This topic is very interesting again. Here we are using cavitation. Cavitation म्हणजे अल्ट्रासाउंड. आय थिंक तुम्हाला पता रहेगा अल्ट्रासाउंड इज okay. In medical field also ultrasound is used. So we are using this ultrasound that is for the preparation of graphene nanocomposite. Nanocomposite म्हणजे addition of two different materials in one, and that is forming composite material. And here we are using graphene. Graphene, it is actually from carbon nanomaterial. So it is from carbon. So if you see nanoparticles, nanomaterial, already आपण आता बघितलेलं आहे already. So here very small size. First is your you can say just a minute.
और एवढा डेंजर कार्यक्रम आहे आणि रोल नंबर नुसार कोणाचं इंट्रोडक्शन करून द्यायचं आणि एक शॉर्ट व्हिडिओ बनवायचा. मार असाइनमेंट प्रत्येक सेशनला हजेरी.
सर थोडं म्यूट
हजेरी
करता
नाही
का?
दिली तर चांग बरं रे नागेन बांधे पुरे.
Hello. Okay. So nanoparticles, we have 3 nanoscale dimension. That means it is something like spherical. Then a spherical, or you can say cubic shape type of case. Then nanoclay. So that is 2 nanoscale. That means it is like a plate type of structure. So platelet मध्ये सारखा आहे. So then nanofiber is rod type of structure. Then nanocomposite is nothing but it is a combination of two material. One may be organic, inorganic nanocomposite, right? So that is also there. Then here one material that is acting as a matrix. That means it will hold the material. And second material is disperse, right? Just like coating. Coating मध्ये काय होतं की when you are adding nanoparticle, that is mix, right? And every nanoparticle is covered with polymer layer, polymer material. So that is, you can say, nanocomposite. That is here holding material is polymer, suppose organic material, that is a matrix, and another one is reinforcement, that is you are adding, right?
For climate case, etc.
Then nanocomposite is material, right? One phase or any other material or any one material which is in 100 nanometer diameter, or that is the dimension what we have. So properties of nanocomposite generally depends on constituent phases. That means what material you are using, right? Then relative amount, what is the
Sir?
amount you are using? Then geometry of that material which we are adding, that is dispersed phase, shape of the material, then you can say particle size, then you can say particle distribution and particle orientation. Everything is very important to have a good property at the end. So
हे इथं नाही का
nano composite will
मी
offer,
येता येता बघू का तिथं असलं तर धोत्यानी का
then lightweight, design flexibility. So that is very important here.
सर प्लीज मध्ये बोलू नका हो, लेक्चर सुरू आहे.
Okay. So properties of nanocomposite material. So that depends on particle size. Then what is the aspect ratio? That means it is a rod shape or platelet-like structure. Therefore, it depends on the high surface area. So that is very important. So large surface area you will observe in the case of nanoparticle. Then larger surface area enables better adhesion with the matrix. So that is again very important. Then improvement in mechanical properties, right, of the parent material. That means where you are adding this material, and if you disperse, then that will and if you use that mechanical property will improve. Example घेतला आपण PVC pipe, polyvinyl chloride. So if you prepare only with the use of polyvinyl chloride, that pipe is flexible then. But if you add calcium carbonate in that nanoparticle, so its strength will increase. So that's why you can use PVC pipe with the addition of such materials. So its the mechanical strength will improve. Better transparency. Then what is cavitation? That is sonication, you can say, ultrasound, right? So here we are using sound wave, that is, sorry, sound energy. That means sound energy that is passed through the liquid medium. And when it is passed through the liquid medium, right? So at frequency greater than 20 kilohertz, right? So what will happen? That will form a wave in a liquid medium. And that during this particular wave, there is a formation of compression and rarefaction. That means high pressure region and low pressure region. During low pressure region, you can say there is a formation of some bubbles, vacuum bubble, and these bubbles, its size will increase and they will collapse at one stage, right? And because of that collapse, it will generate very high temperature and high pressure, right, at local point. Okay. And if you see this phenomena, the ultrasound is a cyclic sound waves, right, whose frequency is above the limit of human hearing. That means you cannot listen this. Only dogs and dogs and bats can hear this. So in this case, when low pressure region is there, nuclear formation will be there. Then there is a expansion phase. That means during low pressure region, that the bubble size will increase, and then it will attain maximum radius. And after that, collapse of that bubble will take place, and that will create an energy of 10,000 Kelvin, and pressure is around, you can say, 1,000 atmosphere. This is for local point, right? And this for millisecond, for very short time it is getting generated. So this is a phenomenon. So you can say decreasing pressure, okay, and this is increasing pressure here. So in decreasing pressure, cavity will form, and after that, in increasing pressure, that cavity collapse will take place. So there are two types of ultrasonications. One is, you can say, direct sonication. That means we are adding that ultrasound probe in a liquid medium, in reaction medium, right? And it is operated in pulse mode, on-off type mode, right? And that's why it is direct contact. So your cavitation is generated in the reaction medium here. And in indirect sonication, so we have a transducer here, that ultrasound is here, and there is a liquid medium in between, and then reaction mixture is here. So in a that means your ultrasound probe is not in direct contact with this, you can say, liquid medium. So that's why it is indirect sonication. So same thing can be done in hydrodynamic cavitation also. So what happens here, we can use the pipeline. Suppose this is a pipeline. I will go to the next point here. Suppose this is pump, right? And liquid is pumped through this. Liquid याच्यामधून जाईल. And we are putting some obstacle. It एक flange असेल and small hole is created here. And that liquid is passed through the small hole. And because of that, on this side, second side, that means here, on this side, there is a formation of some bubbles. कारण pressure खूप कमी होऊन जाते इथे. If pressure is less, then vapor pressure is that means vapor pressure is less, and what happens, operating pressure is less than vapor pressure, then bubbles will form, and these bubbles will get collapse in this region here, right? And that will generate lot of energy, and you can carry out the reaction. त्याच्यामध्ये you can use this for treatment of wastewater. Different reactions can be carried out by using these, right? So different applications will be there by using this hydrodynamic cavitation, right? And this is as per Bernoulli's theorem, which is in fluid mechanics in chemical engineering. So what are the effect of ultrasound? Because of this cavity collapse, what will happen? See, there is a formation of turbulence, vigorous mixing will be there. Then there is, you can say, heating will be there, shock waves will be there, right? So these are some physical effects. And in chemical effect, we have, due to collapse of bubble, extreme temperature and pressure conditions will be generated. And because of that, your water molecule that will get break into OH radicals and H dot radicals. And these radicals are very active. These are very reactive. And that will have a reaction with different pollutants in wastewater. Water मध्ये जर pollutant काय असतील, त्याच्याबरोबर त्याची रिएक्शन होऊन ते pollutant निघून जातात. At the same time, त्याच्यामध्ये सपोज इफ यू हॅव मायक्रो ऑर्गॅनिझम, राईट, त्याच्यामध्ये जर आपल्याला पाणी चांगलं स्वच्छ करायचं असेल तर सो these radicals will kill the bacteria which is present in water also. So that is one more advantage. So that is very important. So, but in our case, we are using this ultrasound for preparation of nanoparticles, right? For the preparation of nanocomposite. That is because of higher reaction rate. That is the important part of this. And then cavitation can improve the processing. That means if you use ultrasound, reaction that will take place in very less time. आम्ही एक लॅब मध्ये रिएक्शन केली होती, that reaction is from 30 hours to 6 minutes. तर त्याचे that much time reduction is there, right? So, and then this plays very important role in preparation of graphene nanocomposite also. Nanocomposite, I will tell what is graphene nanocomposite after. So these are the key effects of cavitation. So one is localized intense pressure and temperature condition, concentration of energy at particular location, high turbulence, increase reaction rate, right? Highly reactive radical formation will be there. So these are the some key effects in the cavitation zone. Then effect of ultrasound sonication. So that will be, you can say, this is effective contact between the reactive species. So reaction will be very fast. Okay, and then it will provide suitable reaction condition at micro scale, right? Then there is a prevention of combining the nuclei, so agglomeration effect will be very less here, right? And promoting equal crystal growth, that is every particle will be having similar size and shape. Agglomeration of particle will be very less in this case. Very small particle formation is there, tiny particle formation will be there, right? Then you can say monodisperse, that means similar size particle, that formation takes place using this. So if you see this is conventional mechanical stirring for the preparation of molybdenum sulfide nanoparticles. And with the use of ultrasound, you can see very small particles are formed in this case. You can check this. This is a small particle form, right? With the use of ultrasound. So you will form uniform morphology, less agglomeration, right? Okay, so that is the with the use of ultrasound. But in this case, this is something different type of morphologies you are getting. So effect of ultrasonication in preparation of nanocomposite synthesis. So that is effective exfoliation of base material. That means it is layer structure. So one layer is separated, another layer is separated like that. So that will be there. And so every layer is exposed to other compound, other reactant, right? And then reduce particle size, then uniform dispersion, that other component will deposit, it will present on the layer. So it is well dispersed there. Nano engineered material can be synthesized by using this. So this is one example I am putting, that is with the conventional stirring method, conventional mixing. So this is formation of nanocomposite, but these particles are agglomerated here, right? So many particles are present. But if you use ultrasound assisted method, sonochemical, this particle is distinguished, well dispersed particles you will observe here, right? So that is the advantage of ultrasound technique. This is for the preparation of polymethyl methacrylate, calcium carbonate, nanocomposite. This is calcium carbonate and this is polymethyl methacrylate, this layer. So this is another one is that SNO2 is loaded on graphene sheet. So this we have prepared, and with the conventional method we will form agglomerated nature, but with the use of you can say ultrasound, these nanoparticles are well dispersed. You can check this. This is around 5 to 10 nanometer particle size, and these are well dispersed on a graphene sheet here. So coming to another part, graphene, carbon. कोळसा माहिती आहे सगळ्यांना कोळसा. So it is carbon, which is what are the forms of carbon? Carbon will be a graphite that is used in pencil, writing pencil, right? So this is a graphite material. Then another material is amorphous carbon. Then diamond is again a carbon, so which is one of the form of carbon. Then fullerene, this is just like a football type of structure. And this is carbon nanotube. Carbon nanotube, it is tube, it is carbon layer which is wrapped to form a pipe-like structure, that tube-like structure here. So if you see different, you can say different forms. Diamond is something like this type of structure, right? Electrical conductivity is very less, no moving electron, right? And it is hardest material, hard material, and it can be used in jewelry. Then another one is graphite. This is layer structure, one layer, second layer, third layer, right? And that is complete form, that is graphite. So it will have a good electrical conductivity, right? And this is very soft material, right? Soft material, and then it can be used as a lubricant. You can say it can be used as a graphite. That is in pencil also it is used, right? So graphene is, this one layer is separated here. See, this one layer which is present here, it is exfoliated. Only one layer is called as graphene. So which will have a higher electrical conductivity. It is very good. It will have a very good electrical conductivity, and it can be used in catalysis or in other application also. Energy storage devices, energy, right? So as an electrode material and all these things. So another one is fullerene. This is basketball type of structure. It is semiconductor, right? So which can be used in drug delivery, or you can say target cancer cells. So where you can find this application. This is the structure of carbon already we have seen. First one is fullerene. Fullerene is zero dimensional. It is spherical structure. 1D is your this nanotube. This is 1D. One dimensional, the pipe-like structure, tube-like structure. Graphene is 2D. This is 2D structure here, graphene. And graphite is stacked, that is three-dimensional structure. This is one dimensional, this is second, and this is third, right? So this is a graphene two-dimensional crystalline allotrope of carbon, right? So it will be in different form. You can see this is hexagon structure. So 6 carbon atoms, right? Arrange, right? It is honeycomb type of structure. That means मधमाशाच्या पोळ्यासारखं that type of structure you will get here. So graphene versus allotrope, if you see, this is a graphene, this is graphite, this is nanotube, carbon nanotube, and this is fullerene. So it will have great application. Suppose if you see this, if you take a graphite, right? This graphite is, you can say, this is a layer structure. It can be oxidized using NaNO3 or sulfuric acid, right? And then some functional group can be created on this, that is such as carboxylic group, OH group, or oxygen functionalities can be created. That is called as graphene oxide, right? And then suppose if you want to reduce this to graphene oxide, reduce graphene oxide. So we need to remove this oxygen functionalities. So that will lead to the RGO, you can say, reduce graphene oxide. So if you see this properties here, it will have a higher thermal conductivity, higher surface area than any other material. Highest thermal conductivity, that is 5000 watt per meter Kelvin. Diamond is having 2300 watt per meter Kelvin. So it is more than diamond you will get, right? Good mechanical stability, right? It is hardest material. So if you see the case study for this, it is same thing as we have discussed earlier, nanofluid application. But in this case, we have prepared graphene and Fe3O4 is loaded on that. So here, if you see this, this is a graphene sheet. This is a graphene sheet. You can observe this, right? And on this graphene sheet, these particles are loaded here with composite material. So this is Fe3O4 particle, right? So if you see the mechanism, this is Fe3O4 particle which is loaded on a graphene sheet here. So effect of ultrasonification. So if you see in the nanofluid preparation here, you will find uniform dispersion of nanoparticle in a base fluid, de-agglomeration nanoparticle, decreased particle size, monodisperse nanofluid can be prepared from this. Then it will alter the properties like stability, thermal conductivity, viscosity, density. Already we have seen this in previous presentation, right? Enhance heat transfer, right? So that will be another application you will find. So if you see this, that is first one is preparation of graphene Fe3O4, right? In bath sonicator. So for that, we have to prepare graphene oxide first, right? That means graphite is treated with NaNO3 or H2SO4. Then synthesis of graphene Fe3O4 composite is carried out. Its characterization is done. Then preparation of nanofluid. Characterization is done by transmission electron microscopy, XRD, XPS, FTIR, other properties also. Then preparation of nanofluid is done. Then characterization of nanofluid, that is by thermal conductivity and rheological property. And then convective heat transfer study was carried out. So this is your preparation of graphene oxide. It is very systematic way it is given here. Graphite powder, then NaNO3, H2SO4 is added under 4 degrees Celsius. It should be at very low temperature, right? And then you are adding, you can say, KMNO4, potassium permanganate. So that is vigorous reaction takes place, and then oxidation of carbon takes place, and that will create some functional group, that is COOH, OH group, like that it is created. And then distilled water or deionized water can be added. And then if you add H2O2, so that will quench the reaction, that will stop the reaction. And then after filtration and drying, you will get a graphene oxide. So if you want to load this Fe3O4 on this, so for that we have FeCl2 and FeCl3 that can be added, right? And then by addition of ammonium hydroxide, the formation of Fe3O4 nanoparticle will be done on the surface. So for that, what we did, that is addition of FeCl2, FeCl3 and water, that forms one mixture. Another mixture you can prepare by adding graphene oxide, which is prepared earlier, and water. So 20 minutes sonication, so that will form well dispersed graphene oxide, and then it is mixed together, and then again sonication, and then we are adding some ammonium hydroxide, NH4OH, and then you will get a back precipitate at the end if you see this. So that is your Fe3O4, that is graphene Fe3O4 nanocomposite that is formed. So here if you see characterization, so this is UV is visible. So green line that is showing graphene oxide, so which is having characteristic at 229 and 300, right? That confirms the formation of graphene oxide. And another one is RGO Fe3O4 nanocomposite, that peaks are 332 and 250, right? So that is the formation that confirms the conversion of graphene oxide into reduced graphene oxide and loading of Fe3O4 nanoparticles on that. So this is transmission electron microscopy. Already we have seen this is this is 20 nanometer size, and you can see these graphene sheets. So this is well dispersed, and then we are putting some loading some particles, nanoparticles, that is Fe3O4 nanoparticles, and that is nicely deposited on this material. So XPS analysis, if you see, so that confirms the Fe, that is Fe is present there. So here oxidized form, that is C double bond over C single bond. But here if you see, there is a reduction in this case. So reduction in the oxygen functionalities here, right? So more material is C bond, C single bond, or C double bond C. So that is the reduction of the carbon, that is graphene oxide. Then preparation of nanofluid, already we have discussed. This is that graphene Fe3O4 nanocomposite is added, water is added. It is mixed, right, in the presence of ultrasound. That is two-step method we have used. And then we are testing thermal conductivity and rheological properties. So this is the instrument what we have used. That is the KD2 Pro thermal property analyzer. And from that we have calculated the thermal conductivity. And this is thermal conductivity at different concentration of that composite and at different temperature also, right? So you can say this is for water, then 1%, sorry, 0.01%, 0.02, 0.07, then 0.1 and 0.2%. That is, if we add the more nanocomposite material, its thermal conductivity will increase. So this is with respect to temperature and concentration, it is similar graph. This is some empirical statistical analysis we have carried out. Based on the experimental data, we have generated this quadratic polynomial. So that is thermal conductivity as a function of volume fraction of nanomaterial. So that is created, and we observe it is well fitted for all the data at different temperature. This is a rheological property, that is we have tested viscosity, how viscosity is getting changed with respect to shear rate. That is by applying some force, how that viscosity is getting changed. So that part is studied in this case. So this is for, we know that with the addition of nanoparticles, some viscosity increase is there, but it is not drastic. It is a slight increase in viscosity is observed here. Then similar type of setup what we have used, right? Here surface temperature was measured, right? And nanofluid is passed through this, what nanofluid is prepared, and this is a closed loop. And from that we have calculated, studied the heat transfer coefficient and Nusselt number, right? At different concentration of the nanofluid and different Reynolds number. So this is different correlations, and this is what we got, that is Fe3O4, graphene Fe3O4 nanocomposite. And we observe that Nusselt number is increased with the addition of nanocomposite here. So that is for every, for different Reynolds number, different flow conditions. So already we have seen, so in every case, it is observed increase. So in summary, you can say fine deposition or uniform deposition of metal oxide, that is Fe3O4 on graphene sheet. So that is observed, and that is because of enhanced nucleation and solute transfer, because of cavitation that is induced by ultrasound, right? Then reduce particle size, then uniform dispersion of Fe3O4 nanoparticle on RGO, then better properties due to fine dispersion. So that is the another case. Then convective heat transfer studies reveal thermal performance of graphene Fe3O4 nanofluid, right? And we found improved heat transfer coefficient, that is Nusselt number, right? So that is because of improved thermal conductivity, because of Brownian motion in the nanofluid. So one more case study we'll take and then we'll stop. So here in this case, here, if you see this preparation of reduced graphene oxide, and in that we have loaded Ag3PO4 and cerium oxide. So that composite was prepared and which was used for the photocatalysis as a photocatalyst for the degradation of MB dye, right? So in this case, first step is preparation of graphene oxide, second step is preparation of RgO-CuO2, third is RgO, Ag3PO4 and CO2 composite. So similar type of process which is used for the preparation of graphene oxide, which is modified Zimmer's method in the presence of ultrasound. That is as we have discussed in previous case, it is same thing here, and that will form a graphene oxide here. So for that, if you in another case, once you get graphene oxide, then we have to load cerium oxide on that. So for that, 0.5 gram of graphene oxide was added in 30 ml of distilled water. Then it is sodicated for 20 minutes, right? And then cerium nitrate hexahydrate was added to the 30 ml graphene oxide solution. Again, it is sonicated, right? And then 0.24, that is sodium hydroxide, was dissolved in another beaker and kept ready. So what happened then? Sodium hydroxide solution was added dropwise in the solution of cerium nitrate and graphene oxide solution, and then it is sonicated for 20 minutes. So that will lead to the formation of RgO-CO2 composite. Then we have loaded Ag3PO4 on that. So for that, whatever prepared composite, that RgO-CO2 nanocomposite we have taken and then dispersed into distilled water, sonicated for 30 minutes, and then immediately we have added AgNO3 solution in that. So that will then the solution added to this dispersion solution, and then Na2HPO4, that aqueous solution was added. So that will create, that will form Ag3PO4, right? And that is loaded on RgO-CO2 nanocomposite, and that is leading to the formation of RgO, Ag3PO4 and CO2 composite. So this is a mechanism. If you see, this is graphene sheet here. On that cerium OH H2O, that is cerium hydroxide, and here that will lead to the formation of RgO-CO2 composite, right? And in second case, this RgO-CO2 nanocomposite, that rod form, right? In that we have added AgNO3 and NHPO4. So that will lead to the formation of Ag3PO4, which is deposited on RgO-CO2 nanocomposite. So that is well validated from this UV-Vis analysis, right? Then it is GO Ag3PO4 CO2 nanocomposite. You can check, right? This is cerium oxide. This is with magnetic stirring, and this is with ultrasound. And you can observe that with the ultrasound, your band gap is very less in this case. So you can check the TEM and imaging of RgO Ag3PO4 CO2 nanocomposite. So you can check. This is a graphene sheet. You can see this is a graphene sheet here. And on that, these rods are deposited, CO2, and then Ag3PO4 nanocomposite particle is also deposited on this. So this is Ag3PO4, and these rods are made up of, that is cerium oxide. And this is your graphene, right? That is deposited. And you can check. It is well dispersed in this image. So the red color is for Ag. This is greenish color you can find for phosphor. Then phosphorus. Then cerium is for blue, and then carbon is for. So it is. You can observe this is well dispersed material which is prepared by ultrasound, and which is confirmed from XRD analysis also. We can observe the peaks of cerium oxide as well as Ag3PO4, and at the same time the peak which is at around 25 degrees 2 theta angles, that is the confirmation of formation of RgO, right? So, and it is also confirmed some functional groups which are present here. That is the peak around 1323 is cerium oxide, right? Then 1049 is C single bond O, 1670 for C double bond O, right? So that is again graphene oxide. Then at 552 and 952, that is corresponding to PO bonding, so which is coming from PO4 3 minus that functional group. So we have carried out the degradation by using this nanocomposite, and if you use this photocatalyst, that is MB-dye. So it is observed that with the addition of these nanocomposite in the system, so we have prepared the dye solution, right, water base, and then we have added this composite and it exposed to sunlight, and it is observed that its degradation is continuous. So after 120 minutes, it is observed that at 100 mg per liter, so it is almost more than 70% degradation is observed. But if you go to the 400 mg per liter, so almost more than 95% conversion was observed, and it is well fitted by first order kinetics here. So here, initial concentration of dye we have studied. No doubt when there is less concentration, then catalyst is fixed. So reaction rate will be more because pollutant molecules are less in number. But if concentration increases, the pollutant molecule, that is MB-dye molecule, will increase, and your catalyst is fixed in amount. So that will that will give, that means that degradation rate will decrease. But anyhow, it is more than 80%. At different pH, this study was carried out, and it is observed that in basic pH, so degradation rate is very high, and at the end of 1 hour, so almost more than 95% degradation was observed. So this is, we have carried out this degradation at different temperature, that is 38, 45, and 55. And from that, rate constant, by fitting first order kinetics, rate constant was calculated. And then we have applied your Arrhenius temperature dependence, that is K equal to K0 e raised to minus E by RT. And from that, the ln K versus 1 by T, that plot was done, and from that we have calculated the activation energy, that is 39.63 kilojoule per mole. So what is the role in the preparation of graphene based photocatalyst here? So what we observe, intensified and fine and uniform loading of metal oxide and other nanoparticles on the reduced graphene oxide, which is attributed to the enhanced nucleation and solute transfer rate because of cavitation, which is generated due to ultrasound use. And catalyst prepared by sonic chemical method, that is having higher photocatalytic activity compared to the photocatalyst prepared with conventional method, because higher catalytic activity, it may be because of more active site, then uniform loading of these nanoparticles on the RGO sheet, right? So then higher activity, it is because of fine dispersion, smaller size particles, so we will have more active sites, so degradation rate will be more in that case, right? So this is the today's second presentation. So if you see, our research group is working in different research area as explained in introductory session also. Advanced oxidation process, liquid emulsion membrane, photocatalysis. Then cavitation based process we are using for the preparation of nanomaterial as well as nanocomposite. Process intensification, that is another research area we are working. Then microreactor systems for the production of nanomaterials. Then nanofluids for heat transfer application, and solid waste processing for preparation of value-added products. So now we have consultancies from 4 industries, and almost we are succeeded in pilot scale also. We are preparing some value-added products from wastewater as well as solid waste, and we are giving some solution to industry also. So these are the areas where we are working, and we are very well connected with industries, and they are giving different problems. So we are working on that. So these are some questions. If you have any questions, I think I will see those. Yes.
Sir, I'm Dr. Mote.
Ah,
This is CBD method or SILAR method?
it is not CBD, it is ultrasound assisted method, and it is a wet chemical method.
Okay, okay, sir. Thank you, sir.
Yes. Any question?
If anyone has questions, please ask without any hesitation. So, sir, shall I proceed to vote of thanks?
Yes, please.
Sir, really, I'm not exaggerating, but I would like to say you are really playing a vital role, zestful excellence and an indomitable spirits. And you can really inculcate the employability qualities unto the students and researchers also. With these approaches like interdisciplinary approaches, innovative approaches, and scientific approaches, you explode and manifest the incredibility towards your through your presentations. So I request all participants to appreciate and acknowledge and get inspired from such esteemed and eminent persons, because this is also so. Sir, once again, on behalf of HRDC's Malviya Teacher Training Program of Dr. Babasaheb Ambedkar Marathwada Universities, I express sincere gratitude towards your expert and incredible session that will be useful everyone's. Thank you, sir. And I would like to request all participants to take care about your videos and your your audios, whether it is off or on, and in which situations we should take such professional manners, professional attitudes, because we all are professionals. So please, all are requested to take care of this also. Thank you, sir.
Thank you. Okay, sir.
Okay, sir.
Okay, bye.
Nice, sir. Very nice.
Thank you.
Actually, I am from language, but I appreciate your session.
Yes, actually, I have
because you
seen
simplified it, sir.
many people are from different background. Yes.
Nice.
Okay, sir.
Okay, thank you, sir.
Thank you.